Okay, so we just got done with chemistry. We're starting physics. First chapter is on motion and speed. So the goal of today's lab and our notes and whatnot is to describe motion in terms of distance, displacement, speed, and velocity, and hopefully tomorrow move on to acceleration. Okay? So first off, what's motion, guys? If something's in motion, it is what? It's moving. Good. Good, I heard Carrie say it changes its position. Okay? It starts at point A, goes to point B. Now, in order for motion to be documented, we need a reference point. A reference point is just a point where you can say, okay, I was standing right here at Miss Hudak's desk, and the tissue box was right in front of me. And I turned around, and according to this reference point, the tissue box moved. Okay? So movement occurred because I have a reference point, I know where that object started at, and I see where it ended at. Okay. Good job. So how about this? Consider the following. Are we moving? So am I moving?
Not right now. Well, you just...
No, right here. No.
No.
Your turn.
Who says yes? Who says no? Who says yes? Everybody has to vote. Who says yes?
Oh.
Who says no? Okay. Yes is why am I moving?
What? Say that again.
Okay, so consider the following. Am I moving? If so, how fast?
You're not.
Who says yes? Who says no? Okay. What are you using as a reference point?
You standing the way you stand, well, where you're standing at.
Good. Depending on your reference point, I am or am not moving.
Your eyes are moving.
Well, we're just talking about me as an object. So, no, relative to you guys, to my classmates, to this desk, I'm not moving. When you saw me initially, I was standing here, you looked away, turned back, I was still here. I did not move. But what about if that reference point is in space? What is the Earth doing?
Rotating.
Rotating, good. So, according to a reference point in space, I am moving.
You didn't ask on that,
Okay, next we're going to describe two terms, distance and displacement, terms that we often use interchangeably, but they are not the same. So, who can tell me what distance is? That's the easy one. We use that measurement all the time.
How far something is traveled.
How far something is traveled. Perfect. What about displacement?
Distance, direction, object change, position. That one's the second definition.
Yeah, it's on there. But so, distance is the vocabulary word that we know. Displacement, we don't so much know. But Carrie got it right on the nose. It's how far an object traveled. Okay? So, if I started in front of my desk, and remember, each one of these tiles is 1 foot, and I traveled 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is my distance?
10 feet.
10 feet. Now, use this tile as a reference point. Displacement, the definition of displacement is the distance and direction from the starting point. Okay? I start here, and I go 10 feet. What is my displacement?
10 feet.
10 feet. So, my distance and displacement were the same. How about now? Okay, we're going to start here. This is my distance. So calculate my distance.
10 feet.
10 feet.
You're 2 feet back.
20 feet.
So,
10 feet,
so what is the total distance?
20 is the total.
20. Okay, ready? Starting here. What is my displacement?
10 feet forward and 10 feet back.
Close. So where's my reference point? Where did I start at?
Right
Where did I stop at?
there. Back there.
What is my displacement?
0.
0. You were right by saying 10 feet forward, 10 feet backwards. It's almost like we said positive 10, minus 10. Good, so distance, you have to account for all of the places you travel. Displacement, it's basically point A. Turn around, you look again, point B. Okay? I really like this example from your book, so I scanned it in. Exactly what I did. A football player. He starts at the end line, runs up 50 meters, turns around, comes back 20. Okay? What is his distance? Starting 50 all the way back to the 20. What do you guys? Good. 10, 20, 30, 40, 50, 60, 70, 80. He's back on the 20. So 80. Good. You had to account for all the way up and halfway back. What about the displacement?
20.
Just 20. Point A, point B. Good. Okay. I asked you guys yesterday if you've heard of scalar or vector quantities. And who has heard of scalar and vector? Not me. So basically in math and in physics, in an IPC, we use scalar and vector quantities. Yeah. Yeah.
You have calculators with you?
Yeah. No, that's fine.
Ah.
Okay, so we have two types of quantities, scalar and vector. They describe two different kinds of numbers, okay? Now I got this awesome slide from the NASA website which describes what are scalar quantities and what are vector quantities. So a scalar only describes magnitude. It's just a number, okay? Vectors are those arrows that you use in math. They have numbers, magnitude, and a direction, okay? So if I say I traveled 10 feet, what is that, scalar or vector? 10 feet. Scalar, I'm just saying, 10 feet. Magnitude is just a number. I traveled 20 feet south.
Vector.
Vector, good, because it's an arrow. Think of it like this. When I just give you a number, it's just an object. It's just a chunk, okay? It's scalar. A vector, you guys know as arrows. You need to know what direction you're going, okay? Scalar, vector. So before I try the next slide, distance is a what? 10 meters. Which one?
Scalar.
Scalar, it's just a number. Displacement, 20 yards north. Good. So you see that, let's see, length, area, volume, speed, mass, they're all scalars. Because we don't know which direction they're going, okay? But we need to know displacement. We want to know, where did it end up? 10 meters north. Direction, velocity, which we're going to go over, and acceleration, which hopefully we'll get to tomorrow. Okay. So how do we measure motion? And this is included on your note sheet. Distance in order to travel. Good. So what is something you travel in every day? A car. How fast do you go?
About 65 miles an hour.
Yeah, it depends.
So you go 65 what?
Miles per hour.
Miles per hour. If you ever forget the units of speed, how to calculate speed, what speed is, just think about a speed you know. 60 miles per hour. You have to go certain miles, you have to go a distance, and you have to go per hour, a certain time. So speed is a rate. It's not a set number, it's a rate at which an object travels. The speed depends on the distance and the time. Therefore, the formula is distance divided by time. And like we said, it's a scalar. It's just a number. There's no direction. Now, units are huge. We use units all the time now. Okay? Distance, what are the units for distance? SI unit.
Meter.
The meter. What are some other distance? Centimeters, kilometers.
Millimeters.
We often use feet and inches, but SI uses meters. Time. How do we tell time?
Seconds, minutes, hours,
Seconds,
days.
minutes, hours. Perfect. Therefore, if speed is distance divided by time, Stephen, what is the units for speed? we're not, no, we're using SI units now. What are some units for speed? You know a distance and you know a time. Yeah, kilometers per second. You will be doing some speed calculations, and then I might actually ask you to do conversions. So I might give you a distance in meters and ask you to convert it into kilometers. So that's one thing we need to start practicing also, depending on what math you've had. Okay, this is also on your notes. There are 3 types of speeds. There's a constant, average, instantaneous. Don't even look at the definitions. What's a constant speed?
Going like cruise control.
Cruise control. Are you changing?
No.
No, you're not changing. Average speed. You're taking an average. Tell me about taking an average.
You add them all up and divide by the number.
Yes. So technically, it's not an exact estimate, but an average. Okay? You might go a little faster some places. You might go a little slower. So you're taking an average. But instantaneous, what is that?
At an instance.
Good.
At one point in time.
Good. Okay. The way you are going to describe motion and speed is through a distance time graph. This is how your tax presents it to you. This is how everybody basically describes speed. We're going to graph it on a distance time graph. So, distance is the dependent variable. Who remembers from chapter 1 what independent variable is? What is an independent variable? Independent.
It doesn't depend on nothing.
The one thing that does not change, it doesn't depend on anything. What is dependent?
Depends on the independent.
Dependent depends on the independent. Okay? If you totally forget where to put the distance, where to put the time, just always think, the bottom has to be time. Because even if you don't go anywhere, time still moves on, right? It wouldn't make sense that time went up the vertical axis, no. So, distance is always the vertical, time is always the horizontal, okay? And distance is the dependent variable, okay? So the distance depends on the time. The time doesn't depend on the distance, right? Time moves by itself. It doesn't depend on the distance. But the distance depends on the time, okay? If you say it the right way, it makes sense. If you flip it around, it does not. Okay, so we're going to do a quick little demo first. I want at least 2 volunteers. Okay. So what we're going to do is calculate the speed of my little car. Now, I had to try to think about how we can do this without y'all slingshotting a car across the room. Because if I said, let's see who can roll the cars the fastest, they'd be flying everywhere. So what we're going to do, using our, what tool is this?
The meter stick.
Meter stick. So we're going to be metric SI units. We're going to measure 2 meters on this table. We're going to time the car for it to go to the starting point to the stopping point. But the only way to move it, so you're going to have to keep it going all the way to the end of the table. That's how we're going to get our speed.
No,
2 meters.
So,
Okay, so Dylan, come and help us measure 2 meters.
I already measured 2 meters.
You already got it?
Yeah.
Here.
I think you're
And Gary, can you come and take the time? Our 2 contestants, why don't you come back there? Get your straws ready.
Measure from is from right here to her finish.
Why don't you put that piece of tape right here? So this is the start. And now from that point, measure 2 meters.
2 meters. Well, from that point, no.
From this point. Look right here.
Oh.
This point. Right here. Here you go, Dylan.
finger, right, Sharon? Yeah, you. Right there.
What if it won't move when we blow it with the straw?
I tried it, it'll move.
What do you think of that? Using your straw.
Well, I don't have any other cars, so this is the only way I can think of. Okay, so 2 meters is our distance. Let me put up here on the board. Ready? We're going to make a distance time graph. We know our distance, guys, right? So for Marissa and for LaPrey, we got to get the times. We know the distance. 2 meters. Okay. So, contestant number 1. Do you want to just practice real quick?
No, that's...
Come on now,
you.
to the posture.
Here, show us how to do it, Miss Matt.
Oh, yeah.
Let me get you a new straw. Okay, practice real quick. Carrie, you know how to work the time?
Yeah, ma'am.
Now you want to participate.
Here.
But guys, you got to keep it on the table. So you might not be able to blow too hard. Okay, so Carrie is going to tell you to go.
Where's
You,
my gun?
So it's going to be
that
LaPrey
line.
and
Miss
You
Hudak.
might have to run along and keep on blowing
Are
it.
you serious?
Yes!
Oh, man, I don't want to do that.
Nope, you got to do it. Ready?
All right, I'll try.
Carrie, you
On
say,
your mark. Get set. Go.
Look at that.
Oh, you broke it, dude.
Try it.
redo.
I tried.
Nope.
Oh.
On your mark. Get set. And go.
It turned around.
Redo it.
Hey, just keep blowing.
Pretty soon we're just going to use the floor.
Alright. On your mark. Set. And go.
Okay.
Dude.
Now, it's a Lego car. We just got to put it back together. What is the time?
3.53.
Q.
Quentin, go up to the board and graph your speed.
Do what?
Graph your speed. Sharice, why don't you go up to the board with him, and you put the horizontal and vertical axes up on there.
Wait,
So
do I
tell
have
me
to
which
do
one's the
temperature
distance,
check?
which one's the time.
Okay, so that, do I got to do it too?
Yeah.
Yes, we need one more person.
Marissa?
I'll show you.
Hey, Dylan, why don't you come do it?
Okay, why don't you get round 2?
Wait. You need to like draw lines on these things or just something.
You don't quit first. I want you to
Or
draw.
what? What?
I want to blow this car.
Blow.
Blowing is hard.
Marissa's been a dirty girl. What's your... You gonna give me a cookie?
Yeah, I'm going to give you a cookie.
You're gonna want that.
You gotta blow it harder than
I
that.
want you too.
Do we have to check in for our food period class?
No, because we got
Okay.
one try.
But I can't do it.
Come on.
I tried. It went like right here.
Come on, Marissa.
Blow it hard.
I was blowing hard.
Gotta blow it harder than that.
See?
Keep on going.
Keep going.
Oh, well, let me start.
Alright, on your mark. Get set.
Go.
Go.
See?
You could have stuck. There we
One
go.
more time. Last time. Come
I
on.
don't want to do it.
I'm gonna blow. Let me blow it for you.
Hold on. But you got to do it yourself, though.
No, I don't. She said one more contestant, and that was you.
No, that's you.
Oh, bummer.
Alright, on your mark. Set. Yeah.
You get on down.
Okay, LaPrey. See if you can do it.
Oh, wait. You can't use the same straw.
Hi, here you go.
Whose straw was that?
Which one?
It's brand new, bro.
Oh, it's in a wrapper?
Put the buggy right here.
Alright, on your mark.
Ain't even opened the straw yet.
Oh, so you can blow it when it's not. No, don't blow my car.
Okay, come on. We got a bunch of
Mark,
stuff to go through.
set, go.
No, I got it across there for a turn.
What is the time?
4.02.
That's baloney.
4.02. Okay, so Sharice helped me make the graph. She said that the time is on the what axis?
Why?
X.
Horizontal.
Horizontal.
X.
And distance is on the vertical. Good. My units, guys, units are a little hard to define, but since we're only talking about a couple seconds, let's say every 4 makes up 1 second. So they're like 1 second. Oh, I'm sorry. Let's do 2. 1, 2, 3, 4. Okay. Distance. Now, we only have a distance of 2 meters, so let's just say 1 meter, 2 meter. Okay, Quentin. I want you to graph your speed if you, at 2 meters, went 3.5, let's round it to 3.5 seconds. So it took 3.5 seconds to go 2 meters. So, good. You got to stay on the 2 meter mark. And you got to go over 3.5. Perfect. Nope, you draw a point. Now, LaPre, come up here. Guys, put away the car. And I want you to graph yours. And you went 4 seconds. So it took you 4 seconds to go 2 meters. So we're at the
4.02, so it'll be like
4.
4.2.
Perfect. So, who has the faster speed? Quentin. Good. So, guys, the closer you get to the 0, 0, this is the closer speed. I'm sorry. This is the greater speed.
All
The
right.
farther away you go, this is the longer speed. So, if you go 2 meters in 1 second, you're going pretty quick. If it takes you 4 seconds to go 2 meters,
Going pretty slow.
you're going pretty slow. So if you can't remember how to interpret the graph, just ask yourself. Let's see. If I go this distance at this time, I'm going fast. And then if you're going this distance at this time, you're going slow. Now, let's see. Let's interpret some of these graphs, because on these graphs, we have different kinds of speeds. The constant speed we talked about, increasing, decreasing. So what I'm going to do is I'm going to call on you, and you have to tell me what you think is happening with the speed and why, okay? Don't just tell me what you think. Tell me why you think it. Okay. Figure number 1. Is there a volunteer or?
Oh, I called it.
Okay, LaPre. What is happening in figure number 1?
Going up. Wait.
What is going up, though?
The time.
Well, time always increases.
Well,
Now, what is the distance time graph measure?
distance and time. Driving.
So you were right, the speed goes up. So, ready? At 1 second, they're about 1 meter.
Yeah.
At 3, so as time progresses,
Their distance is going up.
good. Can anybody else add on to that?
How do you mean?
Well, are they increasing in speed, or do you think they're staying the same?
They're increasing.
They're increasing in speed. Wait a minute, wait.
Because at first you're staying steady and then it increases. Slow.
Is that going?
Now, but Carrie,
So
you're
they
increasing
speed up
in
and then
speed,
go.
but you're increasing in time too. So what do you think is a good way to decide?
Wait, but if they're
you're
like,
increasing?
if they're going, the only way, well, you can tell if they're increasing their speed if It stays like the numbers are going up constantly.
Well, if the numbers are going up constantly, wouldn't that mean that they're at the same
Average,
speed?
like constant, like cruise control.
Right. So one way we can determine if they are is to pick a point right here and to pick a point, for example, right there, calculate the speeds. So why don't we do that in a little? We got 4 meters per 4 seconds, a speed of 1. And let's look at this one right here, 10, and is this at about 7?
Yeah.
So 10 meters per 7 seconds equals a speed of
10 divided by 7 would be about 1.3.
So they are increasing speed. But do you see how you can't really determine it unless you do the calculations?
Right.
Now, this one right here, this one, some people say, oh, they're staying at the same speed. But
No.
really, as time progresses, the distance doesn't change. So what are they actually doing?
They're just
They're
staying
stopped.
still.
Staying still. Perfect. What about this one here?
As
As
time progresses,
They slow
they're
down.
slowing down.
Good.
And
Good.
what about the top right one?
They speed up and then stay constant.
They're going shoo, and they're just cruise.
Awesome, guys. So we're gonna do some more graphical interpretation. But the best way to determine what's going on is to take points and just calculate the speeds. Okay. Okay. At your seats, we got a couple more minutes left. Let's do the first 3 practice problems on the first side of the worksheet. What I want everyone to do, first off, is put the formula for speed down. In each one of these questions, they're asking you for just speed, okay? But, guys, I can actually give you a speed, give you a distance, and tell me to calculate the time it took. Or I could give you a speed and give you a time and ask you for the distance. So I can manipulate that formula however I want. But right now, you guys are doing motion practice problems number 1. First person who gets it correctly and wants to can put it up on the board. And I just gave my calculators to Rose.
What was the average speed, like, with the formula? Or is speed?
Yes. Always use distance divided by time. Always use distance divided by time. Okay, don't forget units. Pair of units. Write the formula and then show me what you substituted in. Some of you guys, I know you know this stuff and I know it's easy, but I want to see a formula and I want to see you substitute. So I see the formula. Show me which one gets subbed where. So, what just...
There we go.
Put it up on the board. Don't forget the units. Okay? Perfect. Perfect. Everybody should be getting approximately 8.3 meters per second. So you need units right there.
Okay. Oh no. Okay.
Okay, guys, we're only going to do this one problem. The battery's running a little low on the camera. One other thing. Speed will tell you how fast you're going. But most importantly, velocity is one step above speed, where it tells you what speed and direction you're going. Okay? So remember that slide that said, here are scalar quantities, here are vector quantities. Scalar was that lump sum. Vector was something that also had direction. Speed is a scalar. It's just a lump sum. Velocity with direction is a vector quantity. Okay? So, Carrie, what is a scalar quantity?
Isn't the speed and the Distance.
Nope. Scalar.
It's just 1 point.
It's just one lump sum, okay? It's just one magnitude. It's just a measurement. Charisse, what is a vector?
It's a, it's like,
Think of those vector arrows.
it's like here's one thing in a direction.
Direction.
It's like pointing in direction.
Good. Stephen, give me an example of a scalar quantity. What did we just say a scalar was? You don't know? Okay. A scalar quantity is a lump sum. It's just a number. It's just a magnitude. Give me an example of one. Where's that?
A car traveling 400 meters.
400 meters. 10 seconds. Vector. Good. So a vector adds direction. Quentin, tell me a vector quantity.
Can I do another one?
Nope. Vector. Give me a vector. Hint, hint.
It's like direction.
It adds direction. Velocity adds direction.
Velocity.
Okay, before we go, a tornado is 30 minutes from Brelon, moving at 200 miles per hour. Who's going to be scared?
It depends on which direction it's going.
Ah, you guys got it too early. Yeah, guys, it depends on what direction. I could say there is a tornado a mile outside. Are you scared? If it's not going in your direction, guys, sit down to the bell rings, okay?
Oh, I got that one. That one.
Okay, for tomorrow, I want you to finish the note sheet and the practice problems, and then you have 5 multiple choice and 1 graphical analysis question. Okay? You should have the notes filled out. Most people have the notes filled out. 2 of the 3 problems done, and that back sheet is just probably going to be your homework. If you have any questions, ask me during tax.
I did Megan's paper.